I'm going to do an example of computing the Schmidt orthogonalization for a set of vectors. So if you recall, what it means for a set of vectors to be orthogonal is that if you take any two vectors in the set, they meet each other at a right angle. Another way of saying that is if you take any two vectors in the set, their dot product will be 0. That's another, like it's a computational rather than visual way to think about this. So I wrote down kind of the algorithm here, but none of the details. So let's make sure we know what these objects are that we're working with. So what we do is we take a set of basis vectors usually basis vectors for a lattice. So these are going to be, we'll say, in Rn. Maybe it could be in Cn or something else. But basis vectors where we have n coordinates that are all real numbers. And we'll call those x1 through xn. So already I actually do have to make a correction. We don't need our basis to be as big as the space or have as many vectors as there are dimensions to the space. So we'll actually say take a bunch of basis vectors in Rm, and we'll call those vectors x1 through xn with n less than or equal to m. If you're not following, I am just tweaking my variables to make sure everything I say is technically correct. What we need to know is that we're starting with n basis vectors. And then what we do is we use Schmidt orthogonalization to make new basis vectors for the same lattice, and then those new basis vectors are all orthogonal. So we're going to follow the procedure over here. So follow this algorithm. Right here. And end up with a new set of basis vectors that still create the same lattice or span the same lattice. But the difference is that these new ones are orthogonal. And then we're going to call our new vectors, sorry, I'm only partly in the video. We're going to call our new vectors after the orthogonalization x1 star through xn star. So this is the goal of this algorithm. You read this algorithm and it looks like a mess, and then you see examples that have been completed, and those also look like a mess because you have these huge fractions and some of the final answers, and it can be a little overwhelming. So I think the best way to really understand the orthogonalization process is to just take a set of relatively easy to work with vectors and just go ahead and compute the orthogonalization and maybe compute a few other things on the way to discuss the properties of what's going on. So we are going to start with, I'm going to leave this up but erase all of this. So we're going to start with a basis. And we'll write it in matrix form. So we're going to start with 1, 1, 1, 1, 2, 3, 1, 4, 9. So this is really just representing the three vectors 1, 1, 1, 1, 2, 3, and 1, 4, 9. So x1 is 1, 1, 1. X2 is 1, 2, 3. And x3 is 1, 4, 9. I like putting the commas in just so someone doesn't think there's like a number 49 in there for clarity, but you don't necessarily have to for vectors. So these are our vectors, and we want to use them to get an orthonormal basis. So before we can even claim that we have the ability to get an orthonormal basis, we need to make sure that these vectors are linearly independent. You can't make a basis from vectors that are linearly dependent because there's repetition, and the definition of a basis requires that the vectors are linearly independent. So the quickest way to just check that everything is linearly independent is to simply take the determinant of the matrix that we have. So I'm not going to go through the process of taking the determinant of this matrix, but we just need to make sure it's not 0 before we can proceed. So let's call this matrix M. So if we look if you calculate the determinant of M, you would find that it's 2. So therefore non-zero, we have a basis. Check. So the other thing is now we have to make this an orthogonal basis, meaning any pair will give us a dot product of 0. And you can kind of see already that this is not going to be orthogonal if you just kind of, since they're all positive numbers, then if we do a dot product, like 1 times 1 plus 1 times 2 plus 1 times 3, it's going to become a positive number. It won't be 0, or, any 2, 1 times 1, 2 times 4 plus 3 times 9. If you add those again, you're not going to get 0. So we have to use this, we don't have to use this process. This is one process to find a set of orthogonal vectors that still span the same space. So we're going to follow this formula, and I wrote down what x1, x2, x3 are, but let me just denote it here so we have space, but we can still reference back to them. So x1 is 1, 1, 1, and the first step of Schmidt orthogonalization is very straightforward. You take the first vector, you set that equal to the first vector in your new basis. So x1 star, this new basis that we're creating, well, we just set that to whatever x1 is. So that is 1, 1, 1. So we've done the first step. But once you do the first step, we now have to find x2 and x3, and the process does become increasingly complicated. Sorry, x2 star and x3 star, and the process becomes increasingly complicated as we move forward. So, in order to find x2 star, we're going to use this right here, and in this particular case, I is equal to 2. So if I is 2, then, and we're looking for x2 star, we're just going to start by writing down our formula that we have here, plugging in what we know. So x2 star equals xi, which is x2, minus, and then we have the sum from j equals 1 up to I minus 1, but I is 2, so I minus 1 is 1. So the sum from j equal 1 to 1 of mu ij. But actually we know that I is 2, so we'll say mu 2j times xj star. So the Greek letter mu often denotes a scalar multiple, meaning it's just going to be a number that we're going to multiply through to everything in the vector. So plug in what we know. So we have x2 star. Well, we know that x2 is 1, 2, 3. So we'll put that in here. Minus, and then we have the sum from j equals 1 to 1, which just means one term. The one term with j equals 1. So what this becomes is mu 2j, or 2, 1, comma 1, times xj star, which is x1 star. So, yes, I have space to move over to the left. So let's move here. Sorry, I have to make sure I don't leave the line of vision. So x2 star is whatever we get if we do 1, 2, 3 minus mu 2, 1 times x1 star, which is 1, 1, 1. So now we have to figure out what mu 2, 1 is and then calculate this. So mu 2, 1, so I have a little space right here. I'll squeeze in the formula for mu 2, 1, but I want to use a different colored chalk just to give some separation. Okay, that's visible. So mu 2, 1, just to write this out without all the i's and j's, is x2 dot x1 star over x1 star dot x1 star. I'm gonna fall. Okay, so this isn't so bad in this particular case because x1 star is just 1, 1, 1. So really what we have for mu 2, 1 is that mu 2, 1 equals, and then we have the dot product of 1, 2, and 3 dot 1, 1, 1 over the dot product of 1, 1, 1 with itself. So what this becomes is we have 1 times 1 plus 1 times 2 plus 1 times 3. So 1 plus 2 plus 3 gives us 6 for our numerator for mu 2, 1. And then on the bottom we have 1 times 1 plus 1 times 1 plus 1 times 1. So the denominator becomes 3, because 1 plus 1 plus 1. So mu 2, 1 in this case equals 2. I chose this example to be nice. Oftentimes mu 2, 1 can be a very messy fraction. You just have to deal with it and do the computations, but it's not so bad, all things considered. So now we know mu 2, 1. We have the rest of our formula here, except, I forgot this. And we can calculate out what x2 star is. So we end up with, we have 1, 2, 3, minus, and then we're multiplying mu 2, 1, which is 2, through to everything in here. So it's minus 2 times 1, 2 times 1, 2 times 1, 2 times 1. So this means that x2 star ends up being 1 minus 2, which is negative 1, 2 minus 2, which is 0, and 3 minus 2, which is 1. So we have x2 star. It's not a terrible form at all. And you have to do these in order, so once you have x2 star, then we can go and find x3 star. So I'm going to need more space to do x3 star. So I'm going to just write up here, as a reminder, that x1 star is 1, 1, 1, and that x2 star is negative 1, 0, 1. Okay, so this isn't a necessary, I might have made a weird noise in there, my screen turned dark. So it's not necessary to check orthogonalization all the way through, but you can check whether or not you've made a mistake by computing the dot product along the way. And if the dot product doesn't come out to 0, there's a problem because, again, when we orthogonalize something, the dot product of any two vectors should be 0. So I'm just going to really quick compute x1 star dot x2 star, which is 1, 1, 1 dot negative 1, 0, 1. And this dot product is not bad. We have negative 1 times 1, so negative 1, plus 1 times 0, plus 1 times 1. So our dot product becomes 0. And this is good because it means our two vectors that we started with are orthogonal. Our two vectors that we've computed using Schmidt orthogonalization are orthogonal. So now that we know these are orthogonal, which means we're probably doing it right, we can go ahead and figure out x3 star, which is a longer computation. So x3 star, here now I is 3 in this formula over here. So x3 star is given by, we take x3 minus, and then we have the sum from j equals 1 to I minus 1, which is 3 minus 1 or 2, of mu ij, so mu 3j, because I is fixed here, xj star. So there's two terms in this sum. It's going to be a little longer. So yeah, I can come over here. So x3 is equal to, x3 star is equal to x3, so 149, minus, and then we'll have to do j equals 1 and j equals 2. So minus, when j equals 1, we have mu 3, 1, x1 star. And then when j is 2, I'm just distributing the negative sign through to all of the parts. When j is 2, we have mu 3, 2 times x2 star. And of course we know x1 star and x2 star already, so the main part that we have to calculate are these mu's and then put it all together. So in this case, let's do mu 3, 1 and then mu 3, 2. So mu 3, 1 is equal to, we have x3 dot x1 star over x1 star dot x1 star. So on the top we have 149 dot 111. And on the bottom, we've previously done x1 star dot x1 star x3, so we'll just put a 3 down here. And so mu 3, 1 becomes 1 times 1 plus 1 times 4 plus 1 times 9, 9, 10, 11, 12, 13, 14. So we have 14 over 3 for our value for mu 3, 1. So let us keep that for just a second and we'll put it into the formula. So this tells us that x3 star is 149 minus, and then we have 14/3 times x1 star, which is 111. And then we have to figure out mu32. Okay, so mu32, I have to get a little lower. Okay, mu32 is equal to, so we have x3 dot x2 star over x2 star dot x2 star. So x3 is 149. So we end up with 149 dot with x2 star, which is -101. So -1, 0. Sorry, I want to be consistent about my lack of commas. And then on the bottom, we're dotting -101 with itself. So then what we end up with is 1 times -1, so -1 plus 4 times 0 plus 9 times 1. So we have 9 minus 1, which is 8. And then in the denominator, -1 times -1 is +1. So we have +1 plus 0 plus 1. So that's 8/2, which is 4, which is thankfully very nice because a lot of times at this point you'd have some very messy fractions. So mu32 is 4. And since I already have the formula right here, I'm going to just replace. So this is mu32 is 4, and then x2 star is -1, 0, 1. Okay, so now we calculate this out. So we have 149 and this one's going to be like easier to deal with than the one with the fraction, so I'm going to actually move that one forward. So 149, and then let's move this a little forward into here. So let's say plus, I'll put the negative through, 4, 0, -4. So, and then minus, and then this one becomes just 14/3, 14/3, 14/3. So essentially I'm just moving it around, multiplying through, so I have to deal with the fraction last. So 149 plus 40, -4. Well, that gives us a starting point of 1 plus 4 is 5, 4 plus 0 is 4, and 9 minus 4 is 5. Not so bad. And then we have to subtract off this 14/3 bit. So actually, this isn't wrong, but I'm going to put a line through it, and I'm just going to write it as, instead of 5, let's do 15/3, just so that we're working with the same denominator for both pieces. So 5 is the same as 15/3, 4 is the same as 12/3, and 5, again, is 15/3. So we have this minus 14/3, 14/3, 14/3. So at this point, dropping chalk. it's not so bad, except, you know, that I'm not really in the picture anymore. 15 thirds minus 14 thirds is 1/3. I don't know if, can we see that? Oh, we can. Okay, 1/3. 12 thirds minus 14 thirds is negative 2 thirds. And then again, we have a 1/3. So this is our x3 star. And again, keep in mind that this was a much less horrible example than some of them will be. Even if you're only working with 3 vectors, you'll get some nasty fractions sometimes. So, x3 star is equal to, we'll just write it up here, 1/3 negative 2 thirds 1/3. And I'm going to erase this now that we are done with it. And as we started with our first answer our first set of vectors in matrix form, let's just put our final answer in matrix form as well. It seems appropriate to call this new matrix M star because everything else was star. So our new matrix that has been orthogonalized using this process is 1, 1, 1, negative 1, 0, 1, 1/3, negative 2 thirds, and 1/3. And that is our final answer. Although hopefully we can maybe revisit this and talk about some of the properties as well, because you know they're orthogonal, they span the same space, but there's additional properties as well that are of interest. Both the matrices should have the same determinant and so on. So we will maybe do that in a future video.